Hi guys, welcome back to another video. And in this video, I'm going to be explaining you the OSI model and the TCP/IP suite. I'm going to be explaining you what both of these models are and basically how each layer functions in both of the model and all the protocols which run in the respective layers. And also in the end of this video, I'm also going to briefly give you some explain you some of the selected protocols which I feel are very interesting and very exciting to know about. And I've also selected three protocols which are TCP, UDP, and DHCP, which I'm going to be covering extensively in the end of the video. I'm going to be covering about the mechanism of these three protocols, basically how these three protocols work, and what are some security issues regarding TCP, UDP, and DHCP respectively. I'm going to be covering that. So it's going to be a very interesting video. So let's get started with the first thing. So the OSI model. So the OSI in the OSI model basically stands for Open Systems Interconnection. It's basically, as the name suggests, it's basically a model or kind of a standard which was developed by the ISO. ISO stands for International Standardization Organization. So it was basically a model which kind of standardized the way two devices were connected and sharing data amongst themselves. So if you look at the model itself, it looks something like this. It's a 7 layer model in which each of the layer is numbered. So you have layer 1, which is physical, 2 is data, 3 is network, 4 is transport, 5 is session, 6 is presentation, 7 is application. One mnemonic which is very famously used to remember all the layers are please do not throw sausage pizza away. So it makes it very easy for you to remember all the layers. And when we talk about abstraction, basically the closest layer to the user would be the application layer, while the physical layer would be the layer which is farthest from the user, which is basically responsible for sending in the raw bits, or basically the electrical signals, zeros and one, through whatever the channel or the medium is. So going back to our previous slide, in the second point, I mentioned that it is a theoretical model which defines a hierarchical approach to network communication. It's very important to understand that OSI model is just a theoretical model. Practically, it is very scarcely used. In fact, in the entire internet is built on TCP/IP suite, and OSI model is just a very good model to get the idea of how communication happens and basically how the task of communication is divided into segments. The protocols defined in the OSI model are very obsolete, and hence the TCP/IP is used more. But one very good advantage, apart from the fact that the model of the OSI is very useful, another advantage of the OSI model is that it is very useful in error handling. I will give you an example. Suppose that there is a organization which has some fault in the network, and you are the guy who they have appointed to troubleshoot the network. So one thing you could do to make your task very much easier is to use the OSI model and go layer by layer, and checking troubleshooting every layer, which would make your job easier. So maybe you could start from the bottom. You could start from the layer 1, the physical layer. You could check whether all the cables are working properly. You could check whether, if it's a wireless network, you could check whether all the wireless equipments are working properly, if the repeaters are working properly, and if all of them are working properly, you could just scratch off layer 1 from your list. So you could just keep on moving up the layer until you find your problem in whichever layer it's lying. So basically it makes troubleshooting also very much easier. In the next slide, we are going to be discussing the general idea of the OSI model. And what I mean by this is basically we talked about layers. The OSI model, as you can see, has 7 layers. So basically, what defines a layer in the OSI model? There are basically 3 things which define the idea of a layer in the OSI model. These 3 things are the service, the interface, and the protocol. Going one by one, the service basically tells what the layer does, or in other words, what service the layer provides to the layer above it. So let's go back and let's take an example and talk about the physical layer. So if I talk about the service of a physical layer, it could be that the physical layer is basically responsible for transmitting the raw ones and zeros, basically the raw bits, throughout whatever the channel is. That would be the service of the physical layer. Moving on, number 2 is the interface. The interface tells the layer or the process above the layer which we are talking about basically tells how to access that specific layer, or basically what are the necessary parameters that are required and what should be the expected result. So let's go back and talk about the same example. Let's talk about physical layer. So when we talk about the interface of the physical layer, we talk about basically how the layer above it, which is the data link layer in our case, would talk to the physical layer. Basically, it defines the set of rules through which the layer above it, which is the physical data link layer, will talk to the physical layer. The parameters required, or basically what should be the expected behavior of the physical layer, are defined in this section. And third, and the most important definition of a layer, is the protocol. Now, the protocol basically defines how the layer itself works. And very important thing is that any protocol can be used as long as using the protocol gets the job done. Basically, whatever the service which is prescribed for a layer, if that protocol can do that service, all is good. You don't need to use a standard protocol. Maybe you have developed your own protocol, you want to use it in that layer. If it gets the job done and it follows whatever the interfacing laws are, basically whatever the parameters are being passed, it can basically it can properly handle those parameters, and it can basically get the job done. The service, it can provide that properly, then you're all good to go. You don't need to use any standard protocol. You can even define your protocol, even though it's a very hard task, but if you want it, you can do it. Let's take an example. We were talking about the transport layer. So generally there are two preferred protocols. You either use the TCP protocol or the UDP protocol. If you're talking about let's say HTTP, you are using HTTP, you would prefer TCP protocol in the transport layer. But if you're talking about voice over IP or gaming or audio video streaming, you would prefer a UDP protocol. So this basically clears what I mean by using any protocol. It just depends on what you want to achieve from this, from the layer which you're talking about. So these three were the general idea which defines a layer in the OSI model: the service, interface, and the protocol. Moving on, now I basically have made this very gigantic table which basically the first two columns compare the OSI model and the TCP IP suite. And also I want to mention one thing. This is probably the last time we are going to be talking about the OSI model, because the OSI model, as I said in the first slide itself, maybe it's very obsolete. The protocols itself is obsolete, and generally people talk about the TCP IP suite. Even though the OSI model is studied, but it's not very useful. So I made a comparison between the OSI model and the TCP IP suite. So basically, starting from layer 1, the layer 1 and layer 2, which are the physical and data link layers, are basically compiled together, and it is called, in the TCP IP suite, it is called the link layer. The layer 3 network layer is called the internet layer. Transport layer is called with the same name. And very interestingly, layer 5, 6, and 7, which are session, presentation, and application layer respectively, are compiled together, and in the TCP IP suite they are called the application layer. So basically, two things you could notice the differences between the OSI model and the TCP IP suite. Number one is that very obviously OSI model has 7 layers, the TCP IP suite has 4 layers. Another thing which you could notice is the OSI model, all the layers are numbered, but that does not happen in TCP IP suite. The layers are not numbered. Now let's talk about the general functionalities of each layer, and we would be using a reference for TCP IP suite, but you can also use the reference for OSI model. Basically, the functionalities remain the same. Talking about the application layer deals with the communication between the other application and between the user and the application itself. So what do I mean by that? So let's assume that you have made a Python program that uses socket programming to basically communicate between two clients in the same subnet. So let's say there is device A and device B. So basically the communication which is happening through the application itself, that logic or that implementation would fall under the application layer. Now coming down to layer 6, which is the presentation layer. The presentation layer is the layer 6 and layer 5, both presentation and session layer, they are hardly ever used, but let's just talk about the general functionalities. The presentation layer just deals with the semantics of the information transmitted, which could mean the file format or the MIME type, while the session layer, which is the layer 5, deals with session establishment, token management. It could also deal with port management. Let's say you are dealing with an HTTP service, and that would use port 80. You are dealing with HTTPS, that would use port 443. So basically, providing ports to those services would be task that would be found in the layer 5, which is session layer. Now going down, we have probably one of the most important layers in the OSI model, which is the transport layer. A transport layer accepts data from the layer above it, splits the data, and it passes the data down. Also, it chooses the type of service to provide to the session layer. The transport layer is very important, and the protocol also which is used in the transport layer, it's also very popular. It's the TCP and UDP, and we are going to be going into depth about these two protocols, basically how it works. In TCP, we are going to be studying about three-way handshake, and also one flaw in three-way handshake, which is called the SYN DDoS attack. And in UDP, we are going to be studying about UDP flooding, which is another kind of a DOS attack, which basically when used with a malicious intent on a server, can crash the server. So that's for the later part of the video. Going back to network layer, which is layer 3, this layer basically deals with packet routing in the subnet. So basically, like ARP, if you know how ARP works, this would be very clear. I did make a video about ARP cache poisoning, but I did not explain what ARP is. ARP basically is Address Resolution Protocol, which basically deals with routing tables. Basically, it makes a table that routes a certain IP address with MAC addresses. So basically, dealing packets, so packets routing in the subnet becomes way more easier. So all those functionalities, IPv4, ICMP, IPv6, ICMPv6, all of those protocols lie within the network layer. Now talking about layer 2 and layer 1, let's talk about both of them simultaneously, the data link layer and the physical layer. Basically, it deals with transmission error and checks the drowning of a slow receiver. I would like to extrapolate on what drowning of a slow receiver means. Let's say there is a transmitter which is transmitting data at the rate of 100 Mbps per second, and let's say there is a receiver which can only receive data in a speed, let's say 1 MB per second. So there is a net loss of 99 Mbps per second of transaction. So that is called the drowning. That thing is called the drowning. Basically, what happens is when the receiver cannot receive the data in the same pace when the transmitter is basically throwing the data at. So the data link layer is responsible for checking whether this receiver is getting drowned or not, and if it is, it basically tells the transmitter to slow down the process of transmitting data. Now talking about the last layer, which is the physical layer, as I'm probably mentioning this the third or fourth time in this video, but concerned with the transmission of the actual bits over the channel. Now let's talk about the protocols of each layer. So I'm going to be referencing the TCP IP suite for this. So in the application layer, we have protocols such as HTTP, HTTPS, FTP, Telnet, SSH, DNS, SMTP, and POP3. I'm going to be going over some of them in the protocol section. And in transport, we have TCP and UDP. Internet, we have ARP, IPv4, ICMP, IPv6, ICMPv6. And in link, we basically have Ethernet, which is 802.3, and Wi-Fi, which is 802.11, and GSM, which I guess stands for Global Service Mobile something, I don't know, but it's basically mobile, concerned with mobile networks. Now the last column is PDU. What does PDU stand for? PDU stands for Protocol Data Unit. This basically refers to what is the data that this layer is basically working with. So when we talk about the application, presentation, and the session layer, which in the TCP IP suite is collectively called the application layer, that layer is working with the data itself. It makes no change to data. While the transport layer, as I had said in the general functionalities, it accepts data from the layer above it and splits it. So basically, the transport layer splits the data into segments. And the internet layer then further splits the segments into packets, and then the data link layer further splits the packets into frame, and finally in the physical layer the frames are converted into the raw bits which are transmitted through the channel. So we have got that clear, and now differentiating between the OSI model and the TCP/IP suite. So I want you to understand one thing, basically how you define a model. Let's talk about OSI model. There are two things essentially. First is the model itself, and secondly are the protocols which are used. So when we talk about the OSI model, the model itself is, when compared to the protocols of the OSI model, it's still very relevant. People are still taught the OSI model, and as I had said, the OSI model still had some advantages, whether it be in error checking or providing the general ideas, the general layered ideas, which were interface, services, and protocols. These things are available in the OSI model. That's why the OSI model is better than the TCP/IP suite model. But when we talk about protocols, the TCP/IP suite protocols are way much better, and the OSI model protocols are nowhere near to compete. Basically, the entire internet is built on protocols which were described by TCP/IP suite. So when it comes to protocols, TCP/IP suite is the clear winner, but when it comes to the model itself, the OSI model is the better one. Moving ahead, I'm going to be discussing some important protocols, which are: number one is HTTP, HTTPS, FTP, Telnet, SSH, TCP, UDP, ARP, ICMP, and DHCP. And I have starred 4, 5, and 8 because I'm going to be separately talking about these protocols because they are very exciting to know about and very important also. So let me just drink a glass of water. Okay. So starting with HTTP or HTTPS. HTTP basically stands for Hypertext Transfer Protocol, and it basically is a protocol that helps you to fetch data from web browsers and stuff. And the thing with HTTP was that it was very unsafe. Now let's assume that you are using your laptop and you are using a banking site. The thing was, when you use HTTP, all the data between your laptop and the router is sent in plain text. So let's say there is a malicious user on your network. He could use a tool like Wireshark. He could use a packet analyzer, and he could analyze all the data which is being sent to and from your device and the router, which would include your banking details. So you don't want that to happen. So that's why HTTPS was introduced, which basically S stands for secure. What this basically does, it tackles the problem of clear text transformation by basically encrypting the data. Now let's move on to FTP. FTP stands for File Transfer Protocol, which basically works on port 21. And by the way, HTTP works on port 80, generally talking about, and HTTPS works on port 443. Talking about FTP, FTP stands for File Transfer Protocol, which generally works on port 21. And as the name suggests, it's basically used for downloading files from remote servers, and that's it. And number 3, we have Telnet/SSH. So Telnet is basically a protocol which is used to remotely control another device. Basically, this is what Telnet is used for. But then again, just like HTTP and HTTPS, Telnet was not very secure. In fact, Telnet was made by some university students because they wanted to have their way around something, so it wasn't really built with the perspective of security. But SSH, which basically stands for Secure Shell, is basically the continuation of Telnet, which is way more secure than Telnet, and hence people nowadays use SSH, and Telnet is now obsolete. Number 4 is TCP, which stands for Transmission Control Protocol, and it basically is a protocol which is used when you want a connection, reliable transfer. And UDP, on the other hand, is used when we want a connectionless protocol, and it stands for User Datagram Protocol. I'm going to be going over these two. Number 6 is the Address Resolution Protocol. I think I mentioned it before. This basically is used for routing in the subnet. It maintains the ARP tables. In fact, if you are on Windows, you could just open up CMD. You could type in ARP space -A to check your current IP table, current MAC ID and IP addressing tables. This is basically the responsibility of ARP to maintain this table. It basically caches these things so that it makes the routing in the subnet more easier. Number 7 is the Internet Control Message Protocol, or which is also called the ICMP protocol. This protocol is essentially used when we want to ping something. Let's say you have your own private website, not a private website. Let's say you have a public website, okay? And what do you do to see if the website is alive or not, if the website is up or not? Of course, you could go to the link of it and you could check it, but another way would be to open CMD and ping your website. If your website's name is, let's say, yourwebsite.com, you could just type in ping yourwebsite.com, and if you fetch a genuine reply from it, that means the host is reachable. But if you receive no reply from it, it just means that the host or your server is dead. So basically that is what ICMP is used for. It's like ICMP protocol, I had read somewhere, it's like hello for the networking protocol. It's like kind of a hello. Number 8 is DHCP. DHCP stands for Dynamic Host Configuration Protocol. This protocol is very interesting because it deals with assigning of new IP addresses to new devices. Let's say that you have bought a new phone and you connect that new phone to your home's router. So basically, when you go to the properties, you go to Wi-Fi settings, you see that your phone has been automatically assigned an IP address, which is the local IP address, of course, but that assignment basically is done by DHCP. It uses a process which is called a DORA process. I'm going to be discussing about all of these processes in the further slides. So that is why DHCP is very important and it's very interesting to learn about. So let's move ahead. So now we are going to be talking about TCP protocol, and the transmission control protocol. So number 1, it's a reliable connection-oriented protocol. So basically, for device A and device B to talk with TCP, there has to be a connection made between A and B before they talk. They allow byte stream from one machine to be delivered to another machine without error. Now I would like to focus without error. Basically, when we talk about TCP, it allows data from one machine to be delivered to another machine without error. While the next protocol which we are going to be talking about is UDP, in which error handling has been given no priority. The main priority of UDP is quick transmission of data. Now let's talk about the functionalities of TCP. Number 1, segments the byte stream into discrete messages, and when at destination, it reassembles the received messages into the output stream. Number 2, handles the flow of control, tries to not drown the receiver. Drown is the phenomenon which I had explained previously. TCP is now used by FTP, HTTPS, SSH, and SMTP. So SMTP is Simple Mail Transfer Protocol, which basically is an email protocol, kind of an email protocol. So these are protocols in which you would not like to have any kind of loss of data, right? When you use FTP or HTTPS or SSH, basically, you would not like to have any kind of loss of data. So this is when the TCP is preferred. The TCP works on the mechanism which is called as the three-way handshake. So this is what the three-way handshake looks like. So I'm going to be taking an example of a client-server architecture, which would make things a bit more easier to understand, even though it's a very easy concept. So let's talk about the first step of the three-way handshake is, let's say that there is a client. Let's say you are the client and you want to connect to a server. So in TCP, the first thing you do is you send a SYN packet, SYN packet, which stands for synchronization. So you send a SYN packet to the respective server. And the second step of the three-way handshake is the server responding to your SYN packet with a SYN-ACK packet, which stands for Synchronization Acknowledgement Packet, which gets received by the client. And the third and the final step of the three-way handshake is the client responding with an acknowledgement package. And after this step, the TCP connection is made between the client and the server. One important thing to know about this is, in the implementation of this three-way handshake, there is one grave vulnerability which gives a malicious user the ability to flood the servers with just random SYN packets, and just so that the server, when responds with the SYN-ACK packet, it just keeps on waiting for the third packet, which is the acknowledgement packet, but it receives none. It is called the TCP SYN flood attack. So this is what happened basically. There is a malicious user and it keeps on sending multiple unnecessary SYN packets. So what happens is, when you refer to back to the three-way handshake, for each SYN packet, the server is innocent. It does not know that the client, it thinks that a malicious user is a normal client, and it receives the SYN packet as it is, and it thinks that I have to respond to every SYN packet with a SYN-ACK packet. So it does. You can see over here, the every even though the SYN packets are unnecessary, the server still responds with the SYN-ACK packets, but then it keeps on waiting for the acknowledgement packet. The server keeps on waiting for the acknowledgement packet, and here is the flaw. So the SYN-ACK packets are not acknowledged by a malicious user, and after responding with multiple SYN-ACK, waiting for multiple ACK messages which are not entertained by a malicious user, and thus exhausting the server and making it unavailable to any legit user. So basically this is what happens. If you send a lot of SYN packets, the server responds with a lot of SYN-ACK packets, and it waits for an acknowledgement packet because it thinks there is a normal three-way handshake of TCP happening, but the server is innocent. It does not know that the malicious user is trying to flood the server with SYN packets and just make it wait for acknowledgement packet which it will never receive. So what happens is, the server gets all the resources of the server, gets exhausted. So let's say there is a legitimate user who wants to connect to the server, but the server becomes so slow it's not possible. So this is kind of a denial of service attack, and it's very interesting. Even though it can be easily prevented, I think in future, I'm pretty sure I'm going to be making a video about all the different kind of DDoS attacks. I'm going to be even making videos about TCP SYN flood and stuff, and Smurf attack, which basically is flooding a server with ICMP packets. I'm going to be making that. So there would be a separate video regarding DDoS attacks in the future, which would be very, very close. Maybe I'll release one this week, but let's see. So this is how a TCP SYN flood attack basically works. Now let's talk about user datagram protocol, or UDP. So the first thing is unreliable connectionless protocol. So when people read about UDP, and this is the first thing they read, unreliable connectionless protocol, they think that UDP, then why would anyone use UDP? The answer is because of its speed. The unreliability, and more importantly, the fact that the UDP protocol is connectionless makes the UDP way more faster than TCP. So it is used for one-shot request reply type queries. Basically, the prompt delivery is more important than the accuracy, such as video game or audio transmission. Not video game transmission, video or audio transmission. It does not require three-way handshake like TCP, and data is transmitted directly using a simple request and response frame. There could be loss of data in the final received data, unlike TCP. And in UDP, the packets are referred to as datagram. So basically, if you're using games and stuff, or if you're watching videos, there could be a drop of just, let's assume, a couple of frames, but it would be unnoticeable. So that's why when it comes to video, audio streaming, or voice over IP, those things are designed that even if there are some drop of information, it would still work. So basically, over there, speed is the main priority, which is achieved using a connectionless protocol like UDP. Even in the implementation of UDP, I would like to stress on the fact that it is a connectionless protocol, which makes it vulnerable to UDP flood attack. I have mentioned it here also. This attack exploits the fact that UDP is connectionless, and hence it can be used to flood a server without its prior permission. So basically, it exploits the fact that you don't need to have prior permissions from a server to make it responsive to UDP packets. So this is what happens. Basically, there is a malicious user. It sends multiple spoofed, and I have made this very important, spoofed UDP packets. And when the server receive the spoofed UDP packets from the user, the server has to respond with ICMP packets routed to the spoofed IP address, which does not exist. So basically what happens is, if you have ever used the ping command on CMD or on Linux, or on Linux it does not work, but on Windows, when you ping a host which is unreachable, the system keeps on pinging the host until it receives finally receives a reply from the host. Even if the host is unreachable, it would never be up in 1,000 years, but it would still keep on sending those ICMP packets. So what happens here is the server then responds with ICMP packets routed to the spoofed IP address, which does not exist. Until explicitly configured not to, the server keeps on sending ICMP packets to the unreachable host, which exhausts the server. So basically, it keeps on doing the same thing, but since the IP address is spoofed, it keeps on sending the ICMP packets to random IP address which does not exist. So this is the message which it receives, which is destination unreachable, resending. And basically what it does is it occupies and exhausts all the resources of a server, so a legitimate user cannot use it. Now finally, we are going to be talking about our last protocol, which is the DHCP, Dynamic Host Configuration Protocol, and it's a very interesting protocol. It basically deals with the task of assigning IP address to new devices connected to the network, and it uses something called the DORA process to accomplish the task. Now, what is the DORA process? I've mentioned it before. Now also what the DORA process is. It's basically a 4-step process. The first step is discover, second is offer, request, and then acknowledge. And this process basically is an acronym. The acronym is DORA process, and this process is basically used to assign a new IP address to our device. And this opcode and 1, 2, 3, 4, 5, I'm going to be getting into this. So in the next slide, this is basically the packet structure of DHCP. We have opcode, hardware type, hardware address length, hops, and there are many other stuff. So let's talk about them one by one. The opcode is basically stands for operation code. It specifies whether the message is a request or a reply. So a request, when we refer to our DORA process, the request would be either discover, which is number 1, or the request itself, which is number 3. And a reply would be offer, which is number 2, or acknowledge, which is number 4. So hence I have written over here, for request the opcode is 1 and reply the opcode is set to 2. So that's why for discover and request, if you see, the opcode is 1, and for offer and acknowledge, the opcode is 2. So if you are sending, let's say, an offer packet, this section would be assigned to 2. Now the hardware type, or the H type, is the type of hardware which is used in local network. For Ethernet, it is set to 1. And the hardware length, address length is boring. Hops basically specify the number of devices traveled by the message between the source and the destination. The default value is set to 0 and it is incremented after every relay. The XID, or the transaction ID, is very interesting thing. Basically, it is a random 32-bit number, and every request made by the client has a specific XID. And when the server replies, the XID is checked, and if the request XID and the reply XID matches, it is confirmed that the reply is that of a specific request. It is used to basically match replies with requests, kind of basically used for matching the reply and the request. The seconds field is used to thus, it's very simple, used to represent the number of seconds elapsed since the DHCP process has officially started. The flags field is also very important. It's a 16-bit field in length, but very interestingly, the rightmost 15 bits, all of them are reserved to 0. All of them. Only the most significant bit is used, basically. So it could be either set to 0 or it could be either set to 1. So basically what those zeros and 1 represent, it basically represents what kind of broadcast is happening. If it is a unicast, the rightmost bit is set to 0, and for multicast, the rightmost bit is set to 1. Then now we have the client IP address, your IP address, server IP address, gateway IP address. These things, to explain these things, we have to dive really deep into DHCP and DORA process. But I think I want to do that for another video, so I will leave this over here. But this was it for the packet structure of DHCP, and I hope all of these things are clear. And if you want, you could just look it up on Wikipedia. It would just clear it out. It's not very hard, it's very simple basically. And if you have Wireshark installed, you could just if you have on your home Wi-Fi, you could just forget your Wi-Fi and just connect it back again, and you can just see the DHCP, the DORA process for yourself. That would be very interesting. Talking about the security vulnerabilities of DHCP, basically there are two. I have mentioned only one over here, but there are actually two security vulnerabilities of DHCP. First is the DHCP starvation, which I have mentioned here, and the second one is the DHCP poisoning. Now, DHCP poisoning, in my opinion, is actually a bit too complex for me to write it down in very short. Even if I do write it down in a short, I don't think it could be very easy to understand basically. So I think it deserves a video on its own. So maybe in the future I'll make a video about DHCP poisoning, but I don't think I'm going to be covering it over here right now. So talking about DHCP starvation, basically, DHCP starvation refers to the attack in which a malicious user sends a forced DHCP request package to the server so that all the available IP address is leased to the malicious user, hence making the server unavailable to allot new IP addresses to the new legit users who would want to connect. So let's talk about a subnet. Let's talk about 192.168.15.xxx. So there could be 255 spaces which are reserved. So let's say there is a malicious user that keeps on sending request frames of the DORA process. We have the DORA process, right? Now he is continuously requesting, and he basically runs the script. He first requests for point 1, then when he gets an acknowledgement frame from the server that the point 1 IP address has been leased to you, he then requests for point 2, and then he keeps on doing that thing, repeating that until point 255. And then what happens is all the available space are allotted to one malicious user. So now let's say you would want to connect to this network. There is no available space for you because there is no available unique IP address for you. So this is where this this is where this attack happens. And this is something related to the this vulnerability is related to the implementation of the protocol itself. So there are ways in which you could protect yourself from this attack, but all of those things would be discussed in a separate video. And I think this would be it for this video. And if you found this video informative in any ways, then like my video and please consider subscribing my channel. And if you have any questions, you could comment your questions down in the comment box. I will try to answer it as soon as possible. And thanks for watching, and goodbye.